Hello, I'm Walker Khan, and this is Lab 2, Lines of Charge. The purpose of this lab is to address an issue on its previous iteration involving the behavior between charged pieces of tape, that being the assumption that the tapes themselves were point charges. In reality, we know that our pieces of tape contain charges distributed throughout its entire system. To better reflect this notion, we will follow a line charge model and compare its results with a point charge model. More specifically, we want to find out how each model derives a charge for our pieces of tape and see whether their values differ, ultimately finding the one that better represents the scenario. Before we continue, we need to state some essential principles. Coulomb's law quantifies a force between charged particles. Supporting it is Newton's second and third law of motion, which helps calculate a force value given mass and acceleration, and that every force has an opposite counterpart equal in magnitude and opposite in direction, respectively. To the right is the electric field of a point charge in superposition, which will help calculate the net electric force of all the charges on our line charge model. Here we have the physical model from the previous lab alongside my values. Underneath are the calculations for the force of gravity acting on tape B, which follows Newton's second law, the electric force, following Newton's third law, alongside the charge on our piece of tape we may derive from these values. Note that the charge equations abide by a point charge model rather than a line charge. For this lab, we need to find a new charge value, Q, for our pieces of tape. We can depend on Newton's third law of motion to detect whether the line charge model grants us an electrical force equal in magnitude to our constant gravitational force, given changes in our Q value. A few assumptions had to be made before developing our line charge model. We assumed that each piece of tape had about the same amount of charge, evenly distributed along its length. We also ignored the air resistance on our moving objects. Here is a GlowScript code that helps visualize and calculate our line charge model. Here are the values from the initial data collection. The variable Q currently stores the tape charge value from the point charge model. Other important factors include a variable that alters the number of particles within our system, alongside a loop that iterates the process of displaying the charged particles with their electrical force vectors, finishing off by calculating the net electric force through superposition. With the Q value of the point charge model, we find an electric force not equal in magnitude to the gravitational force, thus not abiding by Newton's third law of motion. Our goal is to find a Q value that satisfies this law through the line charge model. Through trial and error, I found the charge to be 2.934 times 10 to the negative 8 coulombs, which yields us an electrical force value that is relatively close to the gravitational force in magnitude. Knowing this, we find the charge value derived from a line charge model is almost 2 times that of the point charge model. Why would they differ? The point charge model assumes that all the charges of a system are a single point, whereas the line charge model assumes an even distribution of charges and accounts for the superposition of all electrical forces. Therefore, after knowing that our pieces of tape have charged particles scattered throughout the system, a line charge model better represents the electric force each may exert. Thanks for watching.